Good morning, everyone. I'm Qing Guo from Dr. Jeremy Levy's group, University of Pittsburgh. My topic today will be nanoscale control of the charge neutrality point of graphene. As we all know, the two-dimensional electron-gas system is a very fruitful system for investigating quantum and interaction effects. For example, aluminum gallium arsenide heterostructures and also graphene has attracted wide attention in both condensed matter physics and microelectronic device communities. Besides, oxide materials also show an amazing variety of electronic and ionic phenomena at the junctures where layers of different materials meet. Among them, the lanthanum aluminate strongly tightened interface is a very rich 2D system that contains almost all major electrical tuning properties in solid-state physics, such as superconductivity, ferromagnetism, ferroelectricity, spin-orbit coupling, and so on. For the lanthanum aluminate strongly tightened, there is a metal insulator transition when the thickness of LaAlO is reach a critical thickness, that is 4 unit cell. So above 4 unit cell, the lanthanum aluminate is above 4 unit cell, the conductance of the interface will increase dramatically. And also, this metal insulator transition can be tuned by applying baggage. If the baggage is positive, the interface will become conducting, and if the baggage is negative, it will become insulating. More interestingly, with the conductive AFM lithography technique invented by our group, we are able to write and erase nanostructures at lanthanum aluminate strongly tightened interface. The lanthanum aluminate strongly tightened we use has 3.4 unit cell lanthanum aluminate on top of strongly tightened, that is just at the critical thickness. So when we apply positive voltage, we are able to write nanostructures, and when we apply negative voltage, we are able to create a barrier. So we believe this is due to surface proton. So here is an animation shows how the conductive AFM lithography works. So first we write a triangular shaped virtual electrodes to have better contact with gold electrodes, and then we apply positive voltage to the tip to write a nanostructure connecting these two virtual electrodes. So this is a nanowire. And after that, we can apply negative voltage to the tip to create a barrier. So in this way, the conductance between these two electrodes will decrease. Graphene is a zero-gap semiconductor with one type of electron and one type of holes. The charge carriers can be tuned from electrons to holes continuously. This ambipolar electric field effect brings lots of novel phenomena. The carriers in graphene obey the Dirac equation, and this allow people to observe Klein tunneling in the graphene PN junction. Recently, graphene on boron nitride has been reported. The mobility and inhomogeneity has been increased dramatically. So we all know that new physics come from clean system, and this graphene on boron nitride system allow people to see the predicted Hofstadter butterfly and also fractional quantum Hall effect. So what if we integrate graphene with lanthanum aluminate strongly tightened? Since we can create nanostructures on lanthanum aluminate strongly tightened interface, that nanostructures can have effect with graphene. So in this way, we can integrate these two systems together and study the new phenomenon. So here is a side view of the graphene on top of lanthanum aluminate strongly tightened. And here is a top view. So we will fabricate electrodes contacting the lanthanum aluminate interface and also electrodes contacting graphene. We grow high quality CVD graphene in atmosphere pressure. We diamond tune the copper disc with diamond tuning machine to make ultra flat copper disc. And this is a AFM image of the copper disc. The roughness of the copper is under 1 nanometer. And here is a microscope image of that graphene on copper, so we can get a very large domain like 100 micrometer. And then we transfer graphene and pattern it with Heflon. We tried PMMA before, but that will leave a lot of residue. So the step is first we spin coat graphene with Heflon and then dissolve copper in ammonium persulfide, raising the Heflon graphene piece with DI auto for several times, and then put the lanthanum aluminate strongly tightened underneath this piece and lift up the lanthanum aluminate, let the graphene and Heflon rest on top of it, and then spin coat a layer of photoresist and using photolithography technique to pattern a whole bar structure on top of it, and then using oxygen plasma etching to etch the uncovered part of graphene and Heflon away. After that, we resin the Heflon away with acetone and then dissolve Heflon with FC40, and finally we do a AFM contact mode scan to clean the residue of Heflon on top of graphene. Only leave the graphene whole bar structure on top of lanthanum aluminate strongly tightened. Here is how our sample looks like under the microscope. Our sample size is 5 mm by 5 mm, and we have 18 identical devices on one sample. And this is how the graphene whole bar structure looks like. We have 16 electrodes, 8 of them are graphene electrodes, and 8 of them are contacting lanthanum aluminate strongly tightened interface. And this is a zoom-in AFM image, shows that our sample is relatively clean, and we are even able to see the graphene wrinkles. After that, we did some Magnetotransport measurement on graphene lanthanum aluminate strongly tightened heterostructures. So we're able to see the quantum Hall effect, and the mobility of graphene is relatively high. It can be 30,000. After that, we try to write nanostructures on graphene lanthanum aluminate strongly tightened. So this is a design shows the virtual electrodes and one nanowire. After the writing, we can see a conductance jump between these two electrodes, and we did piezoelectric force microscopy at this region, and even under this, the graphene, the nanowire is very clear. So that means we can write the nanostructures through the graphene. After that, we try to pattern a superlattice on the graphene lanthanum aluminate strongly tightened heterostructure and have nanoscale control of the charge neutrality point. So here is a whole bar structure. On the left part, we pattern it with superlattice. The voltage is applied from the tip bias. The lattice size is about 110 nanometer, and the right part is uniformly pattern region, work as a control group. And we measure the both the pattern region and the control group. The longitudinal resistance versus magnetic field is plotted. By comparing these two groups, we can see a huge difference between the pattern group and unpatterned group. So here we have longitudinal resistance as a function of carrier density at 0 Tesla and 5 Tesla. So from this graphs, we can see that actually after the writing, we are able to tune the carrier density and make the and broadening the drag point. So here we have a Langevin diagram plots the magnetic field versus carrier density. So compare this pattern region with the unpatterned region, we can clearly see that the broadening of the drag point. So that means the writing process is able to change the carrier density at graphene. For a short summary, we are able to grow high quality CVD graphene and transfer it to lanthanum aluminate strand and titanate by using high flow layer. We can also write nanostructures by using conductive air family lithography technique and image these nanostructures by piezoelectric force microscopy. And magnetotransport measurements has been done on this electrically patterned graphene region that shows we can programmable control the charge neutrality point.